Meet Barbara. She's a biochemist that researches how blood clots, and she wants the help of a mathematician to develop some tools for her. She describes to us how clots are formed through a series of complex interactions between different proteins, and she wants a tool that allows her to put in the concentration of these proteins, and it will tell her how these concentrations change over time, which she can then interpret to better understand blood clotting. We start by asking Barbara to explain how these proteins interact with one another. She opens up a long PowerPoint going in depth into each of these interactions. She begins by explaining how these proteins freely float around, and when they get near to each other, they have a chance of interacting. She then goes on about how these interactions happen with probabilities related to the free and activation energies in the system, and we begin to doze off a bit. We're mathematicians, so we like to try and keep everything as simple as possible. So because of this, and because we forgot all of the details Barbara actually gave us, we just remember one line. Proteins move about freely and have a chance to interact when they hit each other. We tell Barbara that we'll have a think about what we can do, and this is what we come up with. Imagine a box filled with balls. Each ball represents a protein moving freely around the box, sometimes colliding with other proteins. How does the number of collisions change as we add more balls? Each ball has some probability that it will hit another particular ball in the next, say, second. If there are n balls, then each ball has some probability p that it will collide with each of the other n-1 balls. So each ball collides with p times n-1 balls on average per second. And there are n balls, so there'll be p times n-1 collisions per second. Technically, we're double counting here, since ball 1 colliding with ball 2 is the same as ball 2 colliding with ball 1. So the actual formula should be p over 2 times n-1. And if we're being careful, then we may remember that Barbara said that each collision only had the potential to be involved in a reaction with some probability. So we can include that too. P times q over 2 times n-1. Since p times q over 2 doesn't depend on n, then we can simplify it to alpha times n-1 using Greek letters because we're fancy. Now that we've done a little bit of work, we have a chat with Barbara and ask a couple of questions. One of the questions we ask her is, what's a typical number for how many of these proteins there are in, say, a milliliter of blood? Around a couple of nanomoles, she replies. We give her a puzzled look and she explains what a mole is, and that it means that there's roughly a quadrillion of these proteins in a milliliter of blood. This may start to concern you, but to the eye of a trained mathematician, this is exciting, since it means that we can simplify our model. You see, 1 quadrillion and 1 quadrillion minus 1 are pretty close. So close that we can just say that they're the same. This means that we can move from using alpha times n minus 1 to just alpha times n squared. Much neater. So far, all of our proteins have been able to interact with each other, since we only looked at all collisions. But, like any good mathematician, we want to generalize this so that we can have multiple different types of proteins that interact with each other. Returning to our box of balls, we colour B of the balls blue and Y of them yellow. Now we can run through the same logic that we did in the first case and see that the rate of interactions between blue balls and yellow balls will be alpha times B times Y. This is known as the law of mass action. We can now start making some predictions with a simple application of our model. Imagine you have a box of blue and yellow proteins. When a blue and a yellow protein collide, they can produce a green protein. From our model, we can write something called a differential equation, an equation which describes the rate at which something changes, in this case, the number of the different coloured proteins. The number of green proteins will increase at a rate given by our model, and the blue and yellow proteins will decrease at the same rate, as they get used up in a reaction. This equation is just about solvable, but we will very quickly run into problems where we can't solve these equations, so instead we turn to computers. They can give us an approximate solution, so long as we can tell them how much of each type of protein to start with. It's very common in mathematical biology to run into problems that can't be solved by hand. In fact, it takes a lot of work to find problems that can be solved by hand. So, using computers and other techniques to simplify problems becomes very useful. Time to have a look at the predictions of our model. We can see that the blue and yellow proteins get used up at the same rate, as is to be expected from the model. And once the yellow protein runs out, then the green protein can no longer be formed. We bring our results back to Barbara, but she isn't impressed. She says she already knows how the individual reactions work, and in fact, she's already experimentally measured all of the alpha rates for all of the interactions that she wanted to look at. She tells us to go away and think about how we can combine the effects of multiple interactions. So we go and do exactly that. After some thought, we realise that we don't need to go back to our box of balls and derive a new model. The change in the concentration of a protein will just be the sum of the changes from each interaction. If we use our model for every interaction and then add them together in the differential equations, we can produce a model that captures many interactions at once. Taking this back to Barbara, she's much happier with our work. She now has a tool that can do exactly as she asked. Unfortunately, it's a very complex system with many of these alpha parameters. We asked for Barbara to give us a little bit more time to work on simplifying it, making it easier to add new interactions in future. Looking over the list of interactions Barbara sent us, we spot a common pattern. There are these groups of interactions that consist of proteins joining together and then separating into either the original components or separating with one of them changing. We asked Barbara about this, and she explains that these are enzymes. One protein, the enzyme, binds to another protein, the reactant, and then has a chance of changing it into a new form called the product. Looking through our model, we see that the concentration of the enzyme bound to the reactant, called the complex, very quickly reaches a concentration and then remains fixed. Our mathematician senses are tingling again. We can exploit this to simplify the model. We have a look at the differential equations describing one of these enzyme interactions. The concentrations where the complex doesn't change over time will happen when dC by dt equals 0. Setting this and doing some rearranging, we find the concentration of C where this will happen. We can then plug this value for C into the other two equations. We then do some rearranging again, tidying up with the equations, and writing the rates in a new form. This allows us to ignore the concentration of C. Barbara now only needs to measure these two new rates instead of the 3 she had to measure previously. And we get all of this at the cost of assuming the complex doesn't change over time, which it already was doing most of the time anyway. This is called Michaelis-Menten kinetics. We take this final model back to Barbara to show her what we found. She's very impressed, and happy that she doesn't need to make as many measurements to add new interactions in future. We tell her about the law of mass action and Michaelis-Menten kinetics. As we're finishing telling her this, we realise that we didn't really use any of the properties of proteins to come up with a law of mass action. In fact, the same modelling framework will work for chemical reactions that don't involve proteins, or anything that looks something like balls bouncing around in a box that do something when they collide. Even populations of animals and people can sometimes follow the same dynamics. If you want to look into this more in depth, I've attached some resources into the description.